So it's my pleasure to introduce a doctor, George Miloshevich, who is a Marie Curie Fellow at the KL11, working on an interface between plasma physics and scientific machine learning. We are also very proud to have George as our project manager of the ASAP project. And we see some of the work that has been done there. This includes the development of AI algorithms for autonomous data analysis. So George's research interests include machine learning for space weather and space plasma, physics-informed machine learning, extreme events in environmental data science, turbulence and recollection in plasma. George also holds a PhD from University of Texas at Austin, working mostly on kinetic effects in turbulent plasma, both relying on analytical and numerical simulation. So very happy to have you here, George, today. Please go ahead.
Thank you so much for this warm introduction. All right, so today I'm going to talk about one of the projects in the ASAP, which is part of Work Package 2. I will also very briefly outline what is happening in Work Package 2, which is responsible for various types of machine learning algorithms that we would like to offer to be worked on oh, sorry, I cannot switch the slide. Yeah, I can switch the slide. Right. Right. So this topic has already been introduced. So I think I'm gonna switch to the slide about our team. So in Work Package 2, we have KU Leuven that works mostly on solar image analysis and contributes this to the ASAP project. And then there is enough that works more on in situ measurements and SEP prediction. Okay, so the topics or the topics that are going to be part of this project include the algorithms that were mentioned by Savas, burst triggering and selective downlink for in situ measurements. So today I will talk about specifically the image analysis and particularly the algorithms relating to solar flare identification. Currently the state of the art is to use very simple algorithms that are based on thresholding. This has been implemented on Solar Orbiter. So these algorithms simply split the sun into little boxes and identify if the intensity goes over a certain threshold. And this is useful, obviously, for essentially choosing the most scientifically interesting data. So the algorithm that I'm going to talk about today is based on it's a CNN architecture that we've been working on at KU Leuven. And it uses as an input 193 angstrom AIA image, which comes from SDO. So this is level 2. So as was mentioned in a previous talk, certainly since it's level 2, is not yet applicable completely to the onboard analysis. But our hope is that it can be in the future if we obtain this data and perform some transfer learning. So the input here is 512 by 512 with several convolutional layers, which are then followed by dense layers. And one of the additional things that we provide is the background X-ray flux intensity from the previous 30 minutes. And so here on the figure, you see the plot for the X-ray flux, soft X-ray flux as a function of time. And in the red, you see the flares. In this case, this was a relatively small study in which where we performed training only on a portion of a year and testing on the last part of this year. But we are planning to train on more data quite soon. So the original results without background, since we're trying to predict actually the X-ray flux and use that as an identification for a flare, the original results actually tend to be predicting the background itself and not so much the flares. However, so the flares would be on this y-axis, you see basically the soft X-ray flux over 30 minutes in the future on the logarithmic scale. You can see that at first we were missing the flares themselves, but if you add background then as an input, this actually improves the prediction. So that was the first improvement which we pursued. So this tool was better at predicting 30 minutes ahead than, let's say, I would say, than the 24 hours ahead. So on the right, you see we performed training on labels which were 24-minute averages, and then it was not so good in performance. But then we started using a different approach where we took the hybrid loss. So previously we've been training on a mean square error. In this case, we decided to take an approach from this publication where we basically hybridize it with the mean square error and cross entropy because we are mostly interested in flaring activity. So it's a sort of a threshold which essentially forces the network to use mean square error only if, which you see on the right, if there is a flare, which we define at a certain value. And also what is interesting here is that if you use this weight factor, W2, which is proportional to the intensity of the flare, in effect, what this does is, in a way, oversample the data which has flares proportional to the intensity. So if you integrate, the distribution function with this weight, you will see that each flares are actually equally weighted. So the distribution function is shown here on the right for the flare data. So we use this weight function, and we have dramatically improved the prediction of the flares from the left to the right. So you can see that it's significantly better. Okay. Right. So at this point, we have basically this 10 years of data of SDO-ML data set. As I said earlier, we have performed testing on November and December 2012, but we will perform a larger study, obviously. Yeah, so that's where we are currently. We have an alternative approach, which is called self-supervision, which combines basically some unsupervised learning with supervised learning. This is the project that's carried by Panagiotis. That we'll talk about another project today after me. So in this case, the idea is to use a UNet type architecture and basically attempt to reconstruct the images of the sun and then use the weights of this network, initialize the network with those weights, and perform any of the specific supervised tasks. So this way, what you're doing is representation learning. So you're learning some useful information that could be more generalizable for, let's say, the rare data such as flares. And these are some initial results from the project. So you have the input images here, the ground truth, and the reconstructed image. So the idea is not to completely reconstruct the image. The idea is to obtain Basically, you apply transformations to the input image, deformations. This could be inverting the image, it could be shuffling it could be adding some noise. And you try to train a network that can reconstruct this image. If the network can reconstruct this image, it means that it has learned something about the morphology of such images, which can be useful for various downstream tasks. Okay, so this is an ongoing project. We have some preliminary results here, but it's still too early to apply this directly for flare forecasting. Yeah, so to summarize, I have introduced this algorithm for the nowcasting of flares, which happens through forecasting of the X-ray flux. There is certainly an issues relating to the fact that the observations of Gauss X-ray flux are recorded by different instruments, which are not calibrated in the same way. So therefore, again, there is some difficulties relating to the fact that one has to calibrate them in order to be able to make predictions about the future states. Okay, so the main conclusion here is that you can use this hybrid loss and you can improve the prediction this way. And in the future, we will try to reduce the complexity of this network. So thank you.
Thank you, George. You have 5 minutes for questions, comments.
Yeah.
Oh, sorry.
Yeah, go ahead.
On the first neural network that you showed, the convolutional.
Yes.
So the data that you used there, is it available? Is it publicly available?
Oh, yeah. This is the L2 data. That is SDO ML dataset, which has been used extensively by various projects for either flare forecasting or other types of tasks. It's basically the SDO data that has been prepared for machine learning applications. It has been rescaled to 512 by 512. It's available over 10 years, and you have multiple channels that are available, as well as other types of features that could be of interest.
There's also HMI available.
Yeah, that's right. There's also HMI.
And additionally, the neural network, you mentioned the convolution max pooling and fully connected layers. What activation do you use? So what activation layers do you use?
Yes, there's softmax and ReLU. So it's pretty standard. Is it because you are concerned that some of the activations would be difficult to implement on?
Yeah. Yes, the softmax is in the end, right?
Yes.
So you use this exponential, but you can remove it because the probability is important. Well, I'll talk about it more.
Yeah, that would be very interesting actually for us to learn the requirements for, from you about what types of activation functions we can use, what types of layers we can use. So we have this from work package 2, as you know, of course, we have created this big table where all algorithms have been tabulated and hopefully it's useful information for people working with hardware implementations. Yeah, that was another question.
Giacomo?
Yes.
Yeah.
I wanted to ask in the slide that you showed on the ground truth versus predicted, like the orange and blue curves. If you have like any idea on, or if there is a baseline and how it compares with this type of plot.
Yeah, I think that's we should produce a baseline indeed, because this is is an application of a single algorithm. We can use various types of base. So one could be we could compare to other algorithms that do the same. We should also compare to the persistence prediction, and I think that would be that would certainly be necessary to do in order to because, for instance, a score. Well, one thing we can also we did compute also. So did I write it down? No. Yeah. We wrote a score which we obtained. So like from here, you can then do some thresholding, and we computed an F1 score because this is a stream event, so there is not many of them, and you can't really talk about the mean square error especially because we are not even interested in predicting these. It depends. For some people, it can be a project also about predicting the background at a different time scale. This can also be useful. In this case, I've concentrated on the flare specifically, and the reason I pursue it from this perspective is because I thought it would be. Of course, you can do classification. Like that's another approach. You could do classification as typically is done, and then you would use only cross entropy. But this is an alternative approach where you say, I don't want to discard the information about the intensity of the flare completely. I still want to rely on this because it's a physically useful quantity, but I still care about the extreme values. So how do I do this? You can play with the loss a little bit. That's one way you can do this. Yeah, so we have a score we wrote down, but it's for a relatively short training data. So I think it would be different if we had more data.
Thank you. Giacomo Savas?
Yeah.
I just have a quick comment on the loss function.
Yeah.
I didn't understand exactly how it was computed.
Yeah. So you have this one is for like no flare. This is in case of a flare. It's basically and then you see you have the part that is sort of like cross entropy, like this part. And you have this is what we had originally, which is the mean square error, right? And this part is so in addition to sort of combining the cross entropy with the mean square error, there is this weighting factor here, which is proportional to the intensity of a flare. But then, if since this is a sum over all of the samples, right? It's a kind of a statistical measure. You can think of it as if you are oversampling flares, right? Because it just multiplies that. So you could achieve something like this by oversampling strategy, but actually it would be, I think this is a more clean way of doing this because you just introduce a weighting. You don't discard any data. You don't generate new data that's possibly, because there are lots of resampling techniques like SMODE, like, all of this. If there's a book on imbalanced learning where they use lots of these techniques, and that's valid. One can try to use those methods, but another way is just you add something in your loss function to weigh them appropriately. And then if you look at this weighting factor, and if you assume a distribution function, which you can get from the data for the intensity of the flares, it follows this distribution function. Then you can compute, what fraction of how many flares you like. What's the amount of P flares you get, C flares and MX flares. So you are biasing basically. That's what's happening here.
Yeah, I was just wondering. There is this called weighted mean squared error function.
Yeah.
Probably those are, if not identical, very similar.
I mean, yeah, because it's a weight. Yeah, it's a weight, but it's chosen in a very specific way. Like it's not usually you have an option always not only in PyTorch, I mean in TensorFlow PyTorch to put like a weighted loss, which will just put a number in front of this. I am not sure if you can put a function there. Yeah, I mean you have to look into the implementation, but here I did it like by hand. Basically, I defined the loss function, and I think in TensorFlow it was like this back when I used to do TensorFlow, but in PyTorch it's a little bit more, hands-on. So you write your loss function, and you could do it also in TensorFlow, of course.
Any more questions, comments? If not, then let's thanks George again.
Thank you.